In this paper, we present a novel PRT-based method that uses pre-computed visibility cuts for interactive view-dependent relighting under all-frequency environment maps and arbitrary BRDFs. In this example, we show how our technique faithfully reproduces realistic all-frequency lighting effects such as hard and soft shadows and glossy BRDF reflections. Our system does not require any pre-computed BRDF data, thus the user is allowed to change BRDFs dynamically on the fly. The runtime relighting computation is performed using a GPU algorithm that quickly computes the lighting integral by accessing a dynamically built light tree, pre-computed visibility cuts, and direct sampling of the BRDF. Using our techniques, we guarantee uniform sampling of the lighting and permit fully dynamic BRDFs. In addition, we can easily adapt the same algorithm to include one-bounce direct-to-indirect transfer effects under local lighting. The user is allowed to manipulate the lighting, viewpoint, and BRDFs at full interactive speed. Our algorithm is inspired by the recently proposed light cuts approach and represent illumination using dense and uniformly distributed sample points. These illumination samples are built into a binary tree structure. The leaf nodes represent individual illumination samples, and the interior nodes represent clusters containing all children samples underneath them in the tree. Using this tree structure, we pre-compute and approximate each scene vertex visibility function into clusters that we call pre-computed visibility cuts. These cuts are computed with bounded approximated error using an iterative refinement algorithm. We repeat the same computation for every scene vertex. To account for runtime dynamic BRDFs, we make the assumption that the variation of BRDF within each cluster is small enough such that it can be replaced by a single sample within that cluster. This assumption requires us to limit the size of each cluster. We do so by subdividing the tree until the solid angle subtended by each cluster falls below a predefined threshold. Our runtime relighting algorithm is accelerated using an efficient GPU implementation on NVIDIA G80 graphics hardware. We found this crucial as sampling the BRDF on the fly is expensive. Our pre-computed visibility cuts data are stored as floating point 3D texture on card. To relight, we first update the textures representing the dynamic lighting that is clustered into a tree. Next, we bind a fragment shader that loops over the visibility cut elements belonging to each vertex. The shading color is then computed as the sum of the triple product of the clustered lighting color L, clustering visibility value V, and direct BRDF samples FR that are evaluated on the fly using the dynamic view direction and the representative lighting direction of each cluster. The results are then copied into a vertex buffer to be displayed as vertex colors in the final rendering pass. In the following, we show several more examples captured with our system in real time.